Hello again. In the previous session, we studied about top-down methods. Methods that we would use to synthesize nanomaterials by breaking down larger and bulk materials into smaller ones. In this session, we'll explore bottom-up methods, which include stacking up atoms and molecules on top of each other to make a nanoparticle. So, why we would use bottom-up method? Actually, the reason that we're using bottom-up methods is because we would have more control over the shape, size, and spatial arrangement of atoms and molecules. In the previous method, we didn't handle molecules or atoms. We just broke down our structure into a nanoscaled material. But here, we would stack up our material. We would build up our material atom by atom and molecule by molecule. So let's dive into the widely used methods in this approach to synthesize nanomaterials. The first widely used technique in the bottom-up approach is a synthesizing method called sol-gel. So what is sol-gel method? As its name suggests, we are going to convert a sol, which is an abbreviation of solution, to a gel, which you've definitely heard this term in your everyday life. We call something a gel if it is actually in a state between being a solid and a liquid. The sol-gel method is one of the most popular techniques that we can use for synthesizing nanomaterials. So let's go and see how we do it. At first, we create a solution with the precursor materials solved in that. We call this a sol, the abbreviation for solution. And then we start heating it up and giving it time to react. So we would have our desired gel. What's a gel? A gel is something between a solid and liquid. In this gel, we have our desired product, but be careful. It's not a solid, it's a gel, and we can't use that. So a very important step, let's say the final step of creating our desired product, is drying this gel. And for drying this, we have various methods, and each of these drying methods would lead to very specific features in our final product. The next method for synthesizing nanomaterials in the bottom-up approach is hydrothermal. The hydrothermal method is what its name suggests. We have this water solution, which stands for hydro in our name, and we will apply some extreme temperature and pressure, as the thermal part suggests. So in this method, hydrothermal, we will put our reactions precursors into a sealed container which can actually tolerate high pressures and high temperatures. We have water in the container, and we will start our reaction. We will ignite, we will trigger our reaction by actually raising up the temperature and putting a lot of pressure. And why would we do that? The philosophy behind this method is that our precursors wouldn't react in normal conditions to result our desired product. So we will just put them into these extreme conditions of temperature and pressure so that we will have our product. Let's say under these extreme conditions, our precursors dissolve, which they wouldn't do in normal conditions, and they would react, and then our product will precipitate from the solution. When I say extreme conditions, I mean the temperature can go up to 1000 degrees of Celsius, and our pressure would be as high as 100 atmospheric pressure. Think of a pressure cooker. In a pressure cooker, you put food into high temperature and pressures, and that would make it something to eat. And here, instead of food and instead of making some food to eat, we are actually synthesizing nanomaterials. This method is often used in synthesizing nanomaterials, producing catalysts, used in batteries, and even in medical applications. The remaining two methods for synthesizing nanomaterials are called PVD and CVD. What do these words stand for? PVD stands for physical vapor deposition, and CVD stands for chemical vapor deposition. First, we're going to study PVD method. The PVD method is a common way to synthesize thin layers on a surface. One of the common ways to do PVD synthesis is sputtering. In this method, we firstly create a plasma, usually from argon gas. To put it simply, in this method, we are accelerating argon ions into our target material, which is our desired material for our thin layer. Our target materials, atoms, are knocked off by the argon gas, and then those knocked off atoms would sit on our substrate and make us our desired thin layer. If I would explain this further to you with an example, I would say imagine you're spray painting a surface. When you're doing spray painting, you're just putting paint as a thin layer on the surface. And here, it's the same, but instead of paint, we are using some materials. Our synthesized thin layers are then used in various applications, including solar panels and electronics. What we do is that here we actually put our materials that we want our thin layer to be made of in the form of vapors in the reaction chamber. The reaction occurs between two different materials. For example, gas A and gas B react. And what happens is that their product, a thin layer made of A and B, is formed on our substrate, on our desired substrate. And this is how our thin layer will actually be created.
This is how PVD method works. We're firing argon gas ions which would hit the surface of our material, and then the material's atoms and molecules would land on our desired layer. And this is how we can actually make something.
There are various ways to do CVD. The thing that differs between these different ways is actually the way we trigger and start the reaction. It can be plasma-based, it can be light-based, and many other ways. And each of these methods have its own advantage and disadvantage. CVD is used to make nano-thin layers in electronics, semiconductors, and all other coatings which are possible. The next way that we're going to study is co-precipitation method. In this method, we have a solution made of our different precursors, and we add a reacting agent to this solution, and then our product precipitates out of the solution. So the reaction between our reagent, our chemical reagent, and the precursors could be really different. Its core could be some kind of oxidation reduction reactions, or it could be simply a precipitation reaction. But be aware that you should be really careful doing these methods. I guess you know by now that nanomaterials are actually higher in energy compared to bulk materials around us. And you know, when materials are higher in energy, they're actually more willing to react with their surroundings. And this reaction actually can ruin our synthesis method. For example, in this method, in the co-precipitation method, the desired product may not be a nanomaterial anymore. Why would that happen? It's because if you just put the materials to react without anything, any special agent added to prevent these materials to react with each other and to combine, what would happen is that our product would be a bulk material again. Our material would just stick together to make a larger material, and that's how our synthesis may be ruined. To prevent that, we would add something named surfactants. The surfactants are actually some special agents which would keep the materials, our nanomaterials, away from each other. They could work in different mechanisms, but imagine our surfactants to be some molecules with large legs, with long legs and arms. They would stick on top of our nanomaterials, and they would prevent our nanomaterials to be together. They would prevent them to meet, to hug, let's say. They're just there to prevent our materials to be larger in scale, and they're a vital step in synthesizing nanomaterials in almost every solution-based synthesis method. If I want to explain this method a little bit more for you, I will tell you this example. Imagine you're putting salt in a solution, you're dissolving it. You are able to dissolve the salt as long as it doesn't precipitate. And this is exactly what happens here. We're actually adding our precursors, our reagents, into the solution until they cannot be solved anymore, until they're reacted and our product is precipitated out of our solution. But here, instead of salt, we have our precursors and our desired material as the product. This method is used to synthesize various types of materials used in drug delivery, medical imaging, and even catalysts. To summarize this approach, the bottom-up approach, we have actually studied in this session 5 different ways to synthesize nanomaterials. We've studied the sol gel method, we've studied the chemical vapor deposition, CVD, we've studied the physical vapor deposition, or PVD, we've studied co-precipitation, and we've studied hydrothermal method. These 5 methods are the most fundamental methods, are the most common methods for synthesizing nanomaterials in the bottom-up approach. So whenever we need some sort of precise way to synthesize our nanomaterials, we would use the bottom-up method, which we can actually arrange atoms and molecules on top of each other to create our desired product. So in this session, we finished the synthesizing methods. Of course, there are many, many more of them, but for now, it's enough for us. In the next session, we will study and talk about characterization of nanomaterials. We'll study that how can we prove actually that we've made some nanomaterial. So till the next session, take care and goodbye.